Hi, my name is Benjamin Bowman. I'm from the Graph Computing Lab at George Washington University, working with my advisor, Dr. Howie Huang. Today I'm going to talk to you about our work on VGraph, a robust vulnerable code clone detection system using code property triplets. Let's first talk about the problem with copy and paste. As we know, we developers, we love to copy and paste code. Open source repositories like GitHub, Bitbucket, and many others make it very easy to distribute our code to a wide audience. However, this causes a serious problem when a vulnerability is discovered in a widely used open source library, for example, OpenSSL, because it's possible that the vulnerable code in question has been copied, pasted, and even modified in many different functions, files, and projects. Identifying these many vulnerable code clones for security remediation is the very challenging problem of vulnerable code clone detection. There's a problem with the existing code similarity-based techniques for detecting these vulnerable code clones, which is that they often focus on exact or near-exact code clones, which we refer to as Type 1 or Type 2 code clones, but their performance suffers when attempting to detect clones with higher levels of modification. In addition, a recent study found that the majority of code clone vulnerabilities in a variety of software packages were of the Type 3 variant, which means that they had line additions and deletions from the original vulnerable code. So based on this, we set out to build a robust vulnerable code clone detection system, which is capable of identifying these highly modified Type 3 code clones without sacrificing accuracy. Now let's talk about some of the key intuitions behind this work. The first is that the patched code is as important as the vulnerable code when trying to detect non-exact code clones. Let's look at why this is. Here is a simulated vulnerable code segment which reads some input data and based on that input data calls various processing functions. The problem when you consider line additions and deletions is that there is essentially infinitely many similar code segments, most likely even including the patch of this function. So what do we do about this? Well, we have to also incorporate the information from the patched function into our algorithm. Here we see the patched code, which includes an additional size check on the input data to the process A function. By including this information in our algorithm, we can effectively zoom in to the specific code elements that are most related to the vulnerability as well as the patch, which provides a finer-grained view of the necessary code elements a vulnerable code clone must contain. This leads to the second key intuition, which is that the key differences between a vulnerable function and a patched function go beyond simple text-based characteristics. To explain that, let's again look at a simple code example. In this case, a very simple off-by-one style buffer overflow. A simple patch for this would be to just increase the size of the buffer by 1 byte. So based on a text comparison alone, the only difference between these two functions is the buffer declaration, and thus this line could be considered as the most relevant line to the vulnerability. However, it's really the buffer access that must occur in order for the vulnerability to exist. So it becomes clear that in order to accurately represent the differences between the vulnerable and patched function, we need a representation beyond the text which contains the dependencies between elements of the source code. So based on these intuitions, this is how we set out to build our vulnerability representation. First, we convert the vulnerable source code and patched source code into code property graphs using the open source tool Joern. This is a very expressive representation of source code that can be generated without the need for compiling the code. Here's an example of a simple function and its representation as a code property graph, which contains a combination of the nodes and edges from the abstract syntax tree, the control flow graph, and the program dependence graph. Next, in order to avoid expensive graph matching algorithms, we sample the code property graphs of both the vulnerable and patched function and generate code property triplets of the form source, relationship, destination. These triplets represent explicit relationships between code found in the code property graph. For example, the fact that x greater than min controls the call to the output y function. We generate additional triplets abstracting the nodes to their node types rather than their raw source code. For example, abstracting the output y call to the general call expression, or the x greater than min code to equality expression. This provides our representation the ability to model the vulnerability even when the underlying source code has changed. Finally, we generate our positive, negative, and context code property triplets as follows. If we let V be the set of all code property triplets from a vulnerable function, and P be the set of all code property triplets from a patched function, then we define the positive triplets as V take away P, negative triplets as P take away V, and the context triplets as V intersection P. Intuitively, these sets of triplets represent the key relationships found in the vulnerable code, the patched code, and the shared code for a particular vulnerability. The table shows example positive, negative, and context triplets for the vulnerable and patched functions on the bottom of the slide. We can see the positive triplet captures a key relationship of the vulnerable function, which is that the call to x greater than min directly controls the call to output y. Similarly, the negative triplets capture a key relationship of the patch, which is that y less than max now directly controls the call to output y. Also, we can see that the context triplets capture relationships that are general to both the vulnerable and patched function, such as the variable x is defined based on a call to the input function. Now, since our vulnerability representation is based on sets of triplets, we can build a simple and efficient matching algorithm based on set overlap between our vulnerability representation and an unknown target function. We first match against the context triplets on line 2 to see if the necessary function context exists for this vulnerability to occur. Next, we match against the positive triplets on line 4 to see if the necessary vulnerable code elements exist as well. And finally, we match against the negative triplets on line 6 to see if this function is possibly already patched to this particular vulnerability. Now let's talk about our evaluations. We compare with 4 other popular code similarity-based techniques. The rough auditing tool for security, or RATS, and Flaw Finder are 2 pattern-based techniques that rely on predefined patterns of vulnerable source code. VGRAPH is a hashing-based technique, and ReDeBug is a sequence-based matching technique. For our dataset, we followed an approach similar to VGRAPH and mined vulnerabilities from GitHub for 8 popular open source repositories, for a total of over 1,000 vulnerabilities as shown in Table 2. This provided our seed vulnerability dataset for VGraph, VGRAPH, and ReDeBug. For our testing dataset, we downloaded code clones of the vulnerabilities in our seed dataset by mining functions from previous and subsequent versions of the codebase, totaling nearly 6,000 vulnerable and patched code clones, as shown in Table 3. These are our results when applying all the techniques to the full test dataset. We can see that the pattern-based approaches provide some of the worst performance, indicating that they are not sufficient for vulnerable code clone detection. We can see that VGRAPH is the most precise of the approaches, which is expected as they are based on a precise hashing technique. However, both ReDeBug and VGraph find significantly more true positives than the other approaches, with VGraph finding the most, leading to the best F1 score. Our test dataset included a large number of exact code clones, and thus, next we zoomed in and limited the results to only those functions with known modifications from the original. Again, we can see that VGRAPH is the most precise, however with significantly worse recall, leading to the worst F1 score of the 3 techniques. VGraph again has the best recall and thus the best F1 score on this dataset. Here we are looking at the same result set as previously, however this time broken down by number of line modifications, ranging from 1 to 10. This shows a similar story, with VGRAPH again being very precise, yet ReDeBug and VGraph having better recall and thus better F1. And again, we can see VGraph having the best F1 of the bunch at all levels of line modification. This is yet another view of the previous results, this time broken down by code clone type. If you remember, the clone type essentially means the complexity of modifications that occur to the clones, with type 4 having the most complex and type 1 the least. We can again see that VGraph provides improved detection performance at types 2, 3, and 4 code clones over the comparison approaches. And finally, before I finish, I please ask you that if you found any of this at all interesting, please go check out our paper. There are tons of additional details and experiments, including sensitivity analysis of our matching algorithm, runtime performance comparisons, line-by-line source code case study evaluations, and much more. So please check it out if you're interested. And that wraps up our presentation. Thanks for listening, and feel free to reach out to either myself or Dr. Huang with any further questions. Thanks.